And our next speaker is Steve Shkoller. And the title, as we see, is Geometry of Shock Formation and Maximal Development for Euler. I take it Euler equations, not Leonard Euler.
You can take it either way.
All right. Okay.
I meant Euler equations, but I for some reason like the way that the title looked without the extra word, so it's aesthetic.
Perfect.
All right. So first, let me thank the organizers. It's really an honor to be able to take part in this workshop and to wish Professor Ebin a happy birthday. So this talk is based on a preprint with Vlad Vickl that we're about to post, who's at NYU. And before I start the talk, I actually just wanted to sort of pay a little bit of tribute to Professor Ebin's pioneering work on Euler and on elasticity. I think from the diversity of the talks just in this workshop, we can just see the profound influence his work has had on all of us. But for me in particular, I think that his point of view of looking at fluids in this sort of Lagrangian perspective has pretty much influenced everything I've ever done, I think. And so I just wanted to say thank you, and I'll just leave it at that. So I'm going to talk about the compressible Euler equations. And there's a more general form of these equations. This talk will be based on the isentropic Euler equations, in which the third conservation law for energy is discarded. And it's just simpler to discuss this, but everything I'm going to tell you that holds for the isentropic Euler equations holds for the more general system. And this kind of looks a lot like the incompressible equations. So for those of you who are sort of familiar with incompressible, but not so much for compressible, there'll be a lot of similarities. So the difference is that we have sound waves traveling around. And instead of the pressure being a Lagrange multiplier that's intended to enforce the incompressibility, now pressure's a function of density. And there's this usual gamma gas law where you say that the pressure is 1 over a constant gamma times rho to the gamma. And here U is a velocity vector, P is the pressure, rho is the density. And I'm going to focus on 2 dimensions, even though, again, everything I say in 2 is also true in 3, but it's just easier geometrically to talk in 2 dimensions. So the first thing that I'd like to do is to just change the way these equations are written. Here, it's written in sort of classical, what's called conservation law form. And this is the way one needs to actually solve the equations when studying discontinuous shocks and for a variety of reasons. But when doing estimates, energy estimates, for example, it's really convenient to put it in this symmetric form. And the reason is basically that you have the same transport operator on both the velocity and sound speed equation. So you can just take the sound speed to be rho to the power alpha. Alpha is just another way of writing the adiabatic exponent. So if you're used to gamma being taken to be, let's say, 2 for shallow water, then alpha becomes 1/2. And the sound speed is just rho to the 1/2. And then we rescale it by dividing by alpha. And this puts it into this symmetric form. And what you can see here is if you were doing L2 energy estimates and you multiplied this equation by sigma and this equation by U, and you integrated by parts, you would get cancellation of these sort of derivative loss terms. And that's how one traditionally closes energy estimates for compressible Euler. Now, as I said, the fundamental difference between the incompressible approximation and the full compressible system is that instead of just having vorticity waves, you also have acoustic waves or sound waves. So there are 3 wave speeds that are important to this problem. And I've ordered them from slowest to fastest. So lambda 3 denotes the fast wave speed. And since I'll be talking about shock formation, this is the characteristics associated with this wave speed are what are responsible for compression and shock waves. So this will be the very important wave speed. Lambda 1 is the slow sound speed. This is sort of, you can think of expansion waves moving with this wave speed, if you like. And lambda 2 is just the fluid velocity itself. So this is, in the incompressible setting, this is what we always study. And I'll come back to this point later, but if you sort of want to make the analogy, if you look at characteristics of this middle wave speed, this is really like the Ebin-Marsden approach to fluid dynamics. It's pretty much the Lagrangian flow map. But there's this unit vector here that I'm calling n for now, and I'm not even going to tell you what it is at this point. It's going to be the normal, the unit normal to some surface, but at this stage, it doesn't really matter. But I'll get to that in a moment. So these are the wave speeds. This is the usual wave speed in incompressible. And this is the guy I put in blue is the wave speed for which we're going to form shocks. Now, you need a good kind of data, initial data, to form shock waves. And before I'm very, very precise about this, I just sort of want to give you the picture that you should keep in mind. So this is the initial condition for what I'm going to define as the dominant Riemann variable. We're going to switch to Riemann variables, which are linear combinations of the velocity and the sound speed. And for now, you don't have to know exactly what it is. If you like, you can just think of this picture as being the initial condition for either density or the horizontal component of velocity, whichever you prefer. And the point of this initial condition is that there is a global minimum taking place at the origin for the slope. So here I'm arranging it so that the partial one derivative, so the shock wave is going to move in this x1 direction, or the shock formation process is going to move in this x1 direction. The transverse direction is x2, and not much happens in that direction. And so x1 is the important direction. And what you arrange this data is that it has a maximal negative slope of -1 upon epsilon, where epsilon is some small number. In this picture, it's like 1/10. And then there's a slight quadratic variation in the transverse direction, where that -1 upon epsilon negative slope gets a little bit bigger, but it's still staying pretty big. So this data is chosen, again, I'll be precise about this, in such a way that this really is a global minimum. And if you zoom in, it kind of looks like this. So I'll say this again later, but in the x1 direction, you can take this to be something like minus sine. And in the x2 direction, you can multiply by something like minus cosine. So this data that I'm showing you is something like minus sine of x over epsilon times cosine of y, something like this, plus a constant so that the density is positive. And this is what the derivatives look like. So again, you can see that there's a maximal negative slope right at the origin, and this is the zoom in. Okay, so what happens if you take this kind of data? I'm just going to go to a couple of videos. So show numerical simulations. So this is what happens if you start with such data. You get steepening of this wavefront, and here a shock wave has formed. And to really see what this looks like, it's better to take a side view. So this is sort of like the one-dimensional cross-section. So you're starting out with kind of a steep slope, and then it forms an infinite slope or an infinite gradient. And then at around 1, so right around here, it's formed an infinite gradient. And then it forms a discontinuity, and now the discontinuity grows and propagates like a shock wave. So this vertical line here is sort of the growing shock wave. And I'll show you one more simulation so you can see it a little bit better. So what is happening at this front is that you have this growing surface, hypersurface, along which the velocity, the density, the sound speed, if the pressure, if you had energy, the energy, if you had entropy, the entropy, they all experience jump discontinuities, and they're all being propagated by what are called Rankine-Hugoniot jump conditions. And in particular, you have sort of an infinite succession of blowups. So maybe the first blowup occurs like right around here, and then at a point, and then it just sort of grows into a surface, and there's this succession of gradient catastrophes. And that is a propagating shock wave. So now let me go back to my slides. Now, the thing is, when I go full screen, I can't actually see anybody. So if please feel free to just yell out that you have a question or you want me to say something or, you know, whatever, because I can't really see you. So far, so good? Okay.
Yep.
Good. Okay, so now let me give you the geometric picture. This is how, you know, how one would think from a characteristic perspective. So what does it mean for a shock to occur? So from the Eulerian perspective, even if you're in one dimension and you're just studying the Burger's equation, something shocks when the gradient first becomes infinite. What does it mean from a Lagrangian or characteristic perspective? It means that these blue lines here are the three characteristics. So these are the characteristics associated with this fast wave speed. And what you can see is that they're impinging. So you're starting out with smooth data. Here I'm just showing you in one dimension because it's sort of very clear what's happening in 1D. So you're starting with smooth data here, and these characteristics are just getting closer and closer and closer. And here at this time here is the time of very first singularity. So up to here, the solution is smooth. And then at that instant of time, these characteristics here have sort of met. And that is the very first singularity. Okay, now what's happening after that? Let me just zoom in a little bit here. So this green line indicates the shock curve. Okay. And what these red lines indicate, these are, I'll define these mathematically later. These are where the Jacobian determinant of this characteristic is vanishing. So what's happening is that inside of this cuspy region that's delineated by these two red curves is where the characteristic is actually no longer one-to-one. You can see that it's two-valued. And so I'm going to explain on the next slide what maximal development actually means. But there's some information that needs to be carried from the Cauchy data inside of this region. And then there are certain parts of this region where Cauchy data cannot enter. And so at this stage, I just sort of want to paint a picture that at first, what you can think is that hold on. I'm sorry? Sorry, I didn't hear that.
Did anyone ask the question?
I heard something.
I think just go on, Steve.
Okay, thank you. Okay, so at first, the point is that you might think that maximal development means that
we're in the room. We just disconnected.
Okay. So something happened. The connection dropped.
Yeah, the connection in the room just dropped, but we're back.
Okay.
So
Steve,
we lost about a minute.
So there are two Steves. Steve Shkoller.
Yes.
Can you hear us?
Yeah, I hear you perfectly. So
okay.
so did you lose me on the numerical simulations or on this page here?
Steve Preston.
Yeah, we lost you on this page.
Okay.
Okay, great. Okay, so let me just start over. So basically, what's happening here, the geometric picture of shock formation, is that instead of thinking in an Eulerian sense that the gradient of velocity or density is becoming infinite, you sort of think in a Lagrangian sense, where you view characteristics associated to the fast wave speed as getting closer and closer to one another. And at the point where they first sort of intersect or become infinitely close to one another, that's this point right here. This is the first time, this is the time of the first singularity. And what happens after here is that at this point here, we get a solution which has an infinite gradient. And then instantaneously after that, a discontinuous shock wave forms. And that's this green curve I've drawn here. Now, these red curves are curves where essentially the Jacobian determinant of this characteristic vanishes. And these are bad curves. And the point is that what you might think is that the maximal development of the Cauchy data is basically something like up until that you hit these red curves, because inside of these red curves, you have a 2-to-1 map, and things are no longer well defined. But that's not exactly the case. So let me explain on the next slide. So this is the analog geometric picture that you should now think about in 2 dimensions. Again, we're looking at the characteristic surfaces associated to the fast wave speed. So this fast wave speed is essentially the normal component of velocity plus the sound speed. And I'm not telling you the normal to what yet, but now it's going to be the normal to this particular hypersurface. But in any case, these hypersurfaces are playing the role of these blue characteristic curves. So here, this is the obvious characteristic curve of the fast acoustic 3 characteristic. And here, these are the characteristic surfaces of the fast acoustic wave. Now, what happens here is that they impinge first at a point, and that's the very first singularity. And up until recently, the only results for shock formation were basically to go just up to this time of the first singularity. And what we're trying to do now is to develop a program where we can go way past this time, up to roughly this time, where we capture a succession of infinite gradient catastrophes. Because as soon as this first guy blows up, everything blows up on this cuspoidal paraboloid. And if I zoom in, there's this intersection of this cuspoidal paraboloid with a certain surface. And this cusp, this crease is what we call the curve of pre-shocks. And I'll tell you about that in a little bit more detail. But this whole cuspy crease to this particular cuspoidal paraboloid is analogous to this one point in one dimension where the first singularity occurs. Okay. Now I want to explain a kind of remapping we're going to do. We're going to pick a nice set of coordinates to study this problem so that we can obtain uniform estimates, even though you're going through this consecutive successive blow up one after the other. So gradients are becoming infinite, and yet we're going to obtain uniform estimates in spite of this by a very nice change of variables. So let me explain what's happening now. This is the Eulerian picture. And this is kind of the Lagrangian picture. It's actually what I'm calling ALE, which is arbitrary Lagrangian Eulerian. It's sort of an interpolation between Lagrangian and Eulerian, but it is essentially Lagrangian. So, you know, to place this into context, in terms of historical papers, this image over here is like Leray, and this image over here is like Ebin and Marsden. And I'll explain what this means from this picture here. So here's what happens in 1D. You take initial data of the type I showed you, where you have a maximal negative slope. And then at this time here, the very first singularity occurs. Now, what happens from this first singularity is that three discontinuous hypersurfaces form. This is the shock wave. This blue curve here is the 2 characteristic that's emanating from this first singularity. And this orange curve here is the 1 characteristic, the slow acoustic characteristic that's emanating from this very first singularity. Now we switch to Lagrangian coordinates, and here's what happens. This right leaf becomes this left smooth part of this parabola. This left red leaf becomes the smooth part of the right side of this parabola. This shock curve, which I've drawn as a line in Eulerian, sort of splits into 2 pieces. There's this part, there's this smooth shock piece, and there's this smooth shock piece. And then what I've drawn here is this 1 characteristic emanating from this first singularity. I've drawn it as this sort of smooth orange curve on the left. So why is this important? Now I can tell you exactly what we mean by maximal development. So what's happening is this. If I use a dotted blue line to indicate the 3 characteristic, I can start with this some initial data here, and I can follow the 3 characteristic up to the shock curve. Now, what happens is that there's a jump condition on this shock curve for a real weak solution to Euler, and I can carry information by this 3 characteristic. I can carry information up to the shock. I can compute the shock, and then I can get information inside of this zone here between the shock curve and this 2 characteristic. And now again, I can compute the jump on this 2 characteristic, and I can use the 2 characteristic to carry information into this region here. So what's happening is that Cauchy data is good just up to the shock curve and no further. And that's from the right. Now, from the left, what happens is that I need there's certain information that's only carried by the 1 characteristic. And if I take, this characteristic is the one emanating from the first singularity. If I take a nearby characteristic, it's going to move to the left. So I can't get inside of this region from the left using the 1 characteristic. And so what that means is that information in this region is coming from the right. So first I take initial data and I go up to the shock curve. Then from the shock curve, I use a jump condition, and I can use other characteristics to go inside of here. Then I can use jump information on this characteristic, and I can go inside of here. So I can get to the right of here by getting up to the shock curve from the right. But from the left, I have to stay to the left of this 1 characteristic. So that's what maximal development of data essentially implies. That from the right, I'm going to go up to the shock curve. So remember, the first singularity has occurred up to this time, so things have already blown up. But I continue the solution anyway because this characteristic here still hasn't blown up. It'll be fine until it actually hits the shock curve. And then from the left, I only go up to here. And that's maximal development. So what does it mean in this Lagrangian picture? It means that first you do uniform estimates up to the first singularity. Then on the right, you continue the solution up until you hit the red parabola, and you can go past the shock curve. And then on the left, you continue the solution until you hit the 1 characteristic. And this is the definition of maximal development. So hopefully I've made that slightly clear, but if not, I'll talk more about it in a moment. And are there any questions about this so far, or should I just keep going?
I think you can keep going. Yeah.
All righty. Okay, so here's the picture in multi-D. And again, this is sort of classical Eulerian, and this is what happens when you go to Lagrangian, except for my version of Lagrangian is slightly modified, which is why I call it arbitrary Lagrangian Eulerian. But the picture is the same. So what's happening is for each x1, so remember, the shock is propagating in the x1 direction, or the wave is propagating and steepening in the x1 direction. And then eventually the shock will also propagate in that direction. Now, for each x1, I take a line of data in x2, and that's how I foliate my space at initial time. And then from each such green line, I look at the characteristic surface that emanates from that. So I'll tell you how that's done in a moment. And as that, again, they intersect, and the intersection is this really unsmooth cuspoidal paraboloid. And the crease of this paraboloid is sort of the interesting, it's the curve of first singularities. So essentially, if for every transverse coordinate, for every x2 in the transverse direction, you're finding the first singularity in x1 parameterized by x2. And that's this crease to this paraboloid. Now you can, if you switch to Lagrangian, then what happens is that these initial points just become labels. And in Lagrangian space, everything's a function of the label. So you're just sort of moving vertically upward along these characteristic leaves. And this left side of the parabola, so here what's happening is that a characteristic surface starts here, and it becomes singular when it hits the left side of this parabola. And that coincides to a characteristic surface starting down here and just moving upward until it hits this part of the smooth parabola. And then similarly here, if you start with this characteristic leaf, the characteristics in the solution will be smooth until it hits this side of the parabola, which is equivalent to starting over here and moving up until you hit the smooth part of this parabola. So in some sense, I'll say this more and more, but we're going to work in this coordinate system, which is very Lagrangian-like, and things stay kind of smooth. And I'll be very, very precise with this. So now let me say a little bit about what this means. So what's happening here is that you have acoustic three characteristic surfaces that are impinging on each other. So they start, here I've drawn 4 examples. So they start kind of, these 4 lines are kind of far away from each other. And as time evolves, they're getting closer and closer. And the first shock occurs when the distance between the nearby 3 characteristic surfaces goes to 0. And again, the number 3 here means that lambda 3 is the fast wave speed, and this is the characteristic surface associated with that wave speed. So it's the Lagrangian flow I'll show you in the next slide. It's like the Lagrangian flow of this weird velocity field that's a combination of the physical velocity and the sound speed. And then the 1 characteristic is the slow characteristic, and the 2 characteristic is the fluid velocity itself, and they don't impinge. They're sort of like I've been drawing. For this time interval, they're essentially straight lines. They don't impinge on each other. Okay, so here's the program. So if you look at the way shock theory has been developed in one space dimension, starting in the 50s and 60s with the seminal results of Glim and Lax and going up to De Perna and Bianchini-Brisson and all of the developments in between, the main idea was to study, to prove that you could have weak shock solutions in one space dimension. And because there's no geometry, the natural functional framework was to use something like the space of bounded variation. Now, by I think 91 or 92, Jeff Rausch wrote a paper where he showed that this idea of using something like BV in higher dimensions just doesn't work. And so here the idea is different. Instead of starting with discontinuous data and proving that you have a weak solution in such a functional framework, the goal here is to start with smooth data and prove that in multiple space dimensions, you can first construct a shock, meaning you get shock formation, And then you can actually prove that it can continue as a propagating discontinuous shock wave, which is called shock development. So up to where you get the first set of singularities, that's called shock formation. And starting from there and developing the discontinuous propagating shock wave is called shock development. So that's essentially the program. And I've broken it up into sort of 4 pieces. So A, you start with the smooth data that I've sort of talked about. Let's say we start at time minus epsilon. Right around time 0, you will get the very first singularity. Now, if you think about doing energy estimates or any kind of analysis in PDE, whether it's Euler or your other favorite PDE, it's really difficult to try and find a method where you can continue analyzing the solution past the time of the first singularity. So in this particular picture, even though the solution has become infinite at, on this parabolic surface. So first it becomes infinite here, and then on this little set here, and then on this big set here. And as all of these successive blowups are occurring, you want a way of continuing to be able to get uniform estimates in spite of the blowup. So the idea is to sort of find a way of doing this, establish the maximal development of the Cauchy data, which is what I tried to sort of geometrically or pictorially explain to you a moment ago. So this talk will be parts A through C, but the big program here is to then use the maximal development to then actually do shock development. So we're going to capture this set of first singularities. And then from there, you use that as data to actually propagate a discontinuous shock wave. And this is sort of how we believe one should do this in multiple space dimensions. So let me make some remarks about this. The first remark is that Christodoulou was really the first to realize that some version of this program was necessary to develop a theory of multi-D shock propagation. The second remark is that for those of you who've studied, like Marcello and lots of other people here who've studied free boundary problems and classical free boundary problems in incompressible or even compressible fluids, you basically use the 2 characteristic there, the fluid velocity itself. And often people in our group switch to Lagrangian coordinates following the Ebin-Marsden approach, and we sort of do the analysis in that particular way. And here what's happening is I'm going to sort of follow that framework. What you'll see is that the geometry here is very much influenced by this free boundary point of view, but instead of using the 2 characteristic, you have to use the 3 characteristic, which means that you have to study a completely different set of equations, even though it's still the Euler equation. Again, I wanted to say that the celebrated result of Ebin and Marsden can really be viewed as doing analysis of smooth Euler solutions along 2 characteristics. So I think one of the important observations in that paper was that when you switch to the 2 characteristic in the parlance of this talk, there's no derivative loss and it becomes an ODE. And in some ways, that kind of idea permeates this work as well, even though there's derivative loss. The final remark is that in our previous work, where we went only up to the time of very first singularity, and this is work with Tristan Buckbaster and Vlad Vickel, we use self-similar analysis there. And the idea of using self-similar analysis is that, again, you switch coordinate systems into a coordinate system that is zooming into the singularity. And since you're only interested in the very first singularity, which occurs at a point, self-similar gives you a very beautiful way of just zooming into that particular first singularity, and it makes the geometry much easier because you don't have to worry about the global geometric picture. But as soon as you want to go and develop a maximal development theory, the self-similar idea sort of isn't useful any longer because you really need this global geometry. And that's what I want to talk about next. So here's the picture. Again, this is going to look like, for those of you, again, who've worked on free boundary problems, this will look very, very familiar to you. The idea here is that these characteristic surfaces, whose leaves I've sort of drawn for you, are going to play the role of an a priori unknown evolving surface. that we wish to parameterize and whose geometry is extremely important because it's the normal direction to this a priori unknown characteristic surface, which determines how everything behaves. Now, again, if you recall the Ebin-Marsden paper, you just remove this and you have the Lagrangian flow for incompressible Euler. And these things are geodesics and so forth. But for our problem, we don't want to study the two characteristic. We want to study the fast acoustic characteristic. So the novelty here is that there's this additional geometric complexity. It's even more nonlinear than the usual flow you're familiar with, because there's this normal vector here. And this normal vector is, like I said, it's the normal to this particular characteristic surface along a time slice. So here I've sort of taken a time slice here. So this blue curve here, I've drawn it as a time slice here. And there's a normal vector and a tangent vector. And using the Lagrangian character, if you take the usual Lagrangian approach, if you call this guy here gamma, so it's a function of x1. As I said, for each x1, you pick a little straight line along the x2 axis, and you take a surface that evolves in time from that. So each of these little blue curves is different for every x1. So you have this curve gamma of x1 and at a particular time slice. So here I've drawn the blue curve at this particular time slice. And the novelty here is that it's this normal here you can parameterize by. So we know that there's an induced metric. So you take the eta comma 2, I should tell you my notation. So partial to eta is written as eta comma 2. So if you haven't seen this looks very annoying, but it's just convenient. So eta comma 2 is a tangent vector, and you can define the induced metric as eta comma 2 dot product eta comma 2. And then you can define the unit tangent vector by taking the tangent vector eta comma 2 and normalizing it. And then for the normal vector, you just take a 90-degree rotation. So you have this kind of slightly more complicated version of the flow map for eta, because it's no longer just an ODE, it becomes a PDE. Now it can be precise. Where does this shock occur? So this surface here, this cuspoidal paraboloid, or if you like in ALE variables, the smooth paraboloid, how is it defined? It's the level set where this Jacobian is actually 0. And that's what I've written here. So the well-known Eulerian criteria that the gradient of U, I should put this in absolute value, sorry, I should make this partial 1, goes to minus infinity and gradient sigma goes to minus infinity. This is just a consequence of the Lagrangian picture, which is that the shock really occurs on this paraboloid where the determinant of the gradient vanishes. And this is just another way of saying that these characteristic surfaces are impinging. So again, the idea, develop a new system of variables along eta such that the solution stays smooth for a much longer, larger time interval than the curve, than the initial set of singularities. Okay, so now I've told you about the Lagrangian picture, and now I'm going to switch gears. So one can do this analysis in the Lagrangian picture, but there's a bit of difficulty here in this analysis, which you don't necessarily find in the sort of usual two characteristic analysis. And that is that the gradient of eta in 2 dimensions is a 2x2 matrix. And some of the components are easy to estimate, and some of the components are unnecessarily hard to estimate. So the geometry here basically is such that the shape of things is easy to estimate, and the tangential kind of motion is annoyingly difficult to estimate. And so there's an improved geometry one can take by switching to what we call arbitrary Lagrangian Eulerian, where essentially we will make a tangential reparameterization. So basically, you now say, okay, very close to where I'm interested, this particular time slice of my characteristic surface is a graph over x2. I'm going to represent it as a height function h. And I'm just going to have to choose dynamics for this height function h, and then define a new set of diffeomorphisms, which plays the role of eta in Lagrangian hydrodynamics. So again, if I look at the geometry of this curve, there's the induced metric, which is 1 plus h comma 2 squared. The tangent vector is h comma 2 comma 1. It's the 2 vector, h comma 2 in the first slot, 1 in the second slot. You normalize it to get a unit tangent vector, and then you rotate 90 degrees to get a normal vector. And then you have to pick the dynamics in the right way. And the way there's a way of doing this. And these are the dynamics for this new family of diffeomorphisms. And what this does is two things. One, it keeps the identical shape of the characteristic surfaces, and it has a slight tangential reparameterization. Now you can define the Jacobian determinant, and it turns out with this, what's really nice about this geometry is that it's just the one derivative, the partial one derivative of this height function. And shock formation again occurs when this Jacobian determinant goes to 0. So the rough picture is this. You have something that's vanishing instead of blowing up. Essentially, the Eulerian gradient blows up like 1 over this Jacobian. And to see this, the normal derivative of the Eulerian normal derivative is scaling like 1 over the Jacobian times partial 1 of the ALE variable or Lagrangian variable. And the tangential derivative is completely regular, and it's just like partial 2. So it's a really nice coordinate system, and the sort of singularity is built in. Okay, so now the geometry of maximal development. Let me say a couple of more pictures here. So remember, I told you here that there's this crease. Now, what is this crease? This crease, let me just zoom in. I don't know if you can see this, but there's this cusp along this line here. So what is this line? This line is the intersection of JG, J equals 0 and partial 1 J equals 0. So it's the intersection of this surface here, which is this paraboloid, and this surface here, which is essentially this plane. And it gives you this curve here. Now, what I can do, so in this picture here, that crease becomes this smooth little parabola. And and that tells me for each x2, this is x2 direction now, and this is the direction in which things are propagating. So for each x2, I have this curve where the first singularities are occurring parameterized by x2, and I can extend it as a constant in the x1 direction. So this guy, this red guy is the real paraboloid where everything blows up. And this green parabolic cylinder is just the extension of this curve here all the way is a constant in the x1 direction. And I'll tell you why I'm doing this. Okay, but first let me just sort of now define new variables for you. So now I have to talk about Riemann variables. So this is sort of how you define Riemann variables. So, and I'll tell you why they're defined, but in one space dimension, they're defined because once you switch to these variables, they are themselves just transported by their own characteristics. So in one dimension, this object is transported by the 3 characteristic. This object is transported by the 1 characteristic. And so you can sort of reduce 1D Euler analysis, 1D isentropic Euler analysis to a 2x2 system that looks like 2 coupled Burger's equations. It's really quite nice. But in multi-D, you have to do something a little bit different. So you define this Riemann variable. This is what's called the dominant Riemann variable. This is the guy that's going to cause all the problems, as u dot n plus sigma. Then there's the subdominant Riemann variable, which is u dot n minus sigma. And then this is the tangential component of the velocity, which stays quite smooth and doesn't really bother you very much. This is the object that's going to bother you very much. Now, let me come back to the Euler equations. So what you have to do is you have to differentiate them once. And that's what this comma k means, partial kth derivative of ui. So you have to differentiate them once. And then you have to modify the transport velocity so that instead of being carried by the usual fluid velocity, they're carried by this wave speed, the fast acoustic wave speed. And the price you pay is that you then have to subtract it back off. Now, why do you have to differentiate the Euler equations before modifying the transport velocity? It's because in this new geometry, following the characteristic surfaces, there's derivative loss, which means that if you try to do this without first differentiating Euler, your velocity and sound speed would have one derivative less on them than the geometry already has, and it would be impossible to do the analysis without severe derivative loss. So you do this instead, and because of this, you have to define this new kind of Riemann variable where you take this, you take the gradient matrix. So this is a 2x2 matrix in 2 dimensions. It's the gradient of the velocity. And then you compose with your ALE map. So this is like composing with eta if you're doing Lagrangian. And you have this ALE version of the gradient. And here you take the gradient vector, taking the gradient vector of the sound speed, and you compose with psi, and now you have this gradient vector in ALE coordinates. And then you form this vector of Riemann variables. This is the dominant Riemann variable by taking this 2x2 matrix, contracting with the normal direction, and adding the gradient vector. You do the same thing for the subdominant Riemann variable, and then you do the same thing for the tangential component of this gradient of velocity. Now, you can write the transport, the waves, the 3 wave speed, lambda 3 and ALE variables, and there's this additional transport velocity. This is coming from the tangential reparameterization and going from Lagrangian to Eulerian. But this thing is essentially 0. You can think of it as being 0. So anywhere you see it, you can just ignore it. Okay, so basically, in terms of these variables, this is what the initial data for W naught looks like. And it's exactly this picture here. So to leading order, it's like kappa naught, which is like 1 minus x1 over epsilon plus a little parabolic term in x2. So I've drawn it for you here. And the important variable here is the normal component of this vector, which is essentially a times 0 partial 1 of this object here. And this is what I drew for you in the early slides. So to give you a little dictionary, and I'm almost out of time, so I'm going a little bit fast now. This object here is the only object that's going to blow up. It's the normal derivative of the Eulerian Riemann variable minus a small geometric contribution. This guy is blowing up. It's actually going to go like 1 over the Jacobian determinant. These 5 quantities, which is the normal component, tangential component of Z, normal component of A, tangential component of A, and tangential component of the dominant Riemann variable, they all stay smooth. And that's sort of the punchline. These are the nice variables. Okay, so I'm going to skip the motivation for this. I don't really have time, but the motivation is that in 1D, you can do a computation and you can get an explicit formula for this subdominant Riemann variable. And you can see that it actually remains smooth, even though, so let me just say one thing that's sort of interesting. I told you that in 1D, if you go along the 3 characteristic, these objects are merely transported. and you have this very simple equation for the dominant and subdominant Riemann characteristics, Riemann variables. And what you can see here is that eta x of math ring W is just the derivative of W naught, the initial Riemann variable at time 0, or initial time. And so this combination here, what's important about it is that it's just the initial data. And here you can see that W naught, math ring W, just goes like the initial data, which is roughly -1 over epsilon, divided by this object. And in multiple space dimensions, this object, it's being played by JG, the Jacobian determinant. Okay, so here's what the Euler equations sort of look like in ALE variables. You can take v to be 0 if you like. It's really small. So you have this JG is g to the -1/2 j. So you have this rescaled Jacobian determinant times the time derivative of W, and it's almost transported. You have these lower order terms, and then you have this derivative loss term that I've written in blue. The Z equation is the same, but now you have a real PDE. So you have partial 1 derivatives, and same for A, you have partial 1 derivatives. And sigma is just the sound speed. That's a lower order object. I just put it there for completeness. Now, when you do energy estimates, this guy and this guy combine to exactly cancel out with this guy at highest order. So I put those in blue. So those don't present any difficulties. The difficulties are elsewhere. Okay, I'm getting there. So I'm just going to quickly show you, there's just nice geometric structure. I don't really have time to get into details, but basically you can compute nice evolution equations for the normal, the tangent vector, and for this rescaled Jacobian determinant. And this JG is really playing the role of, in 1D, the derivative of Lagrangian coordinate. And it has a very nice property. This is what the full equations look like. They're beyond hideous. I've sort of written them for you in a sort of simplified way. This is how you scale things for energy estimates. You need 2 powers of JG in this equation for reasons having to do with the fact that this compression gives you both damping and anti-damping. And it's just a technical game of having to beat certain anti-damping. So the more of these you put on, the better, the easier it is to close energy estimates. Okay, now I'm going to go really quick because I'd like to finish in about a minute or two. But I just want to give you a sort of picture because the details are impossible to sort of convey. So the idea is this. You first remap space-time to flatten this green region, this parabolic cylinder. You just flatten it. And nothing happens in the x1 direction. So here, if you look at what's happening in x1, this is the initial data. This green guy here becomes flat. And this parabolic cylinder just becomes a this paraboloid just becomes a parabolic cylinder. Now, the analysis is split into 2 parts. You first do energy estimates up until this green plane. Then you can continue the energy estimates up here until you get to this parabola. And then you do something else on the left, which I'll say in a minute. So here's the norm that we can close the energy estimates with. You have to take 5 of these gradients. So it's basically partial t, partial 1, partial 2. There's an epsilon that you have to put in front of the partial t and partial 1 just to bring things into a nice balance. And then there's some rescaling having to do with the flattening of space-time, but you can just think of the usual space-time gradient. So you apply 5 of them, and you basically get 2 kinds of norms. One is L infinity in time that has a certain kind of weighting by this object which is vanishing. And the other is L2 in time, and this is coming from compression. So compression, even though we're studying a hyperbolic problem, the compression actually gives you signed integrals, which give you L2 in time damping, if you will. And the damping arises by commuting JG around time derivatives. And the basic principle here is that I told you that in 1 dimension, this object is exactly the initial data, the derivative of initial data, it turns out that it's essentially true modulo errors in multi-D. And that because the initial data is like -1 over epsilon, you have this sort of upper and lower bound. Now, I know I'm going very, very fast here, but I just wanted to point out that these are roughly the norms: 5 derivatives of normal components with 2 powers of JG, and 5 derivatives of tangential components with 1 power of JG. And now you can close energy estimates. And the main theorem is this, that you get maximal development. You go all the way up to the flat green parabolic cylinder. Then you can go all the way up to this paraboloid on the right. And then on the left, you go up to this blue surface, which is the one characteristic surface that's emanating from that crease. So we have uniform estimates all the way up to here. We get maximal development of smooth dilute solutions. There's no derivative loss. Let me just sort of end by saying that there's a recent preprint of Abrescia and Speck, where they establish part of the maximal development. In this picture, it would be sort of on this side, just up to this region. And this has to do with the fact that here, partial 1 of JG is greater than or equal to 0. And there's I think they're going to release a companion preprint where they handle this side. Their methods are really quite different. They use Christodoulou's geometric framework. So they have rough foliations of space-time, whereas we have very smooth foliations of space-time. And they have some derivative loss, and to compensate for the derivative loss, there's sort of a lot of derivatives that need to be used. But it's an interesting result that you can take a look at. Okay, I'm not going to say too much about the ideas of the proof. It's basically using new kinds of energy estimates and some nice geometry. What I wanted to end with was basically that once we have the shock formation finished, our goal is to actually do shock development, but I've sort of run out of time. So let me just end by thanking you and saying happy birthday to Professor Ebin, and I'm happy to take any questions if anyone wants to.
Thank you, Steve. Any questions from the audience or the online participants?
Hi, can you hear me?
Yes.
Good. So some time ago, there was some work by Izumiya and Kossioris on shock development for a scalar conservation law in 2 space dimensions. Do any of those ideas come in here? They used more a qualitative singularity theory approach.
No, so we finished a paper about 1.5 years ago with Theo Drivas and Vlad Vikol and Tristan Buckmaster on shock development for 2D Euler under azimuthal symmetry, which essentially reduces you to 1 space dimension. And there you can prove that not only do you get the shock forming, but you actually get these so-called weak singularities that Landau and Lifshitz conjectured. And we gave a precise description of what the solution looks like. Now, I think that's the only full shock development result that's known for Euler at the moment. Christodoulou, the authors you mentioned, and Yin have results for either what's called the restricted shock development problem, which is Euler without conservation of mass and conservation of energy, or for some sort of scalar problems. So the big difference between going from symmetry to non-symmetry is that in symmetry, there's no geometry. And so you really just have to set up the right functional framework and use precise information like the C1/3 regularity of the solution at the first singularity and be able to extend using some clever characteristic approaches together with very nice, fixed point approaches in a good weighted functional framework. What happens in the in multi-D is that now you really have to control the geometry because things are happening in the transverse direction. And so the very first singularity is no longer a point, but rather a curve or a surface in 3 dimensions. And the biggest difficulty is that under symmetry or under scalar, a lot of these scalar conservation laws, sort of toy models, there's no derivative loss. And so you can really look at ODE methods along characteristics, whereas here we have to contend with really horrible derivative loss and find the sort of the right geometric framework to deal with the cancellations. So there's some ideas that are very similar in terms of like how you extend the solution, and in some sense, this picture that I've drawn, that I drew here at the very beginning to motivate things. Sorry for the scrolling, but I just wanted to, this picture here, this is very much a 1D kind of idea that also holds in multi-D. So this idea of how you get to certain regions of space-time holds. And the fundamental difference is that you can no longer just take a characteristic and evolve it the way you can in 1D. And that's where a lot of the difficulty comes in. So I probably said more than you wanted to hear, but that's the answer.
You said more and less, because you also didn't explain why you don't, maybe you explained why you don't cite Izumiya and Kosioris in your bibliography.
So for this talk, the only citation I gave is to the Berisha spec paper, because that's the only other result for maximal development in multi-D. In our actual preprint, we do cite all of the previous work that has occurred in this area.
Oh, okay. I'm only familiar with the Buckmaster paper, and that's not this. In the Buckmaster paper, we weren't aware of that particular result, but we've become aware of it since. Very good. Okay, you answered my question. Thank you.
Okay.
Any other questions?
Yes. So, Steve, can you hear me?
Yes, I can.
Yeah, thanks. That was beautiful. I have a million questions, but I guess for the sake of time, I'm going to stick to one or two. So I'm trying to just translate what you did to some language that I'm slightly more familiar with. So I think I'm seeing your J as like the analog of the inverse foliational density that Christodoulou has. Is that correct?
Yeah. Yeah.
So presumably you have to commute the equations with vector fields that are also weighted by J?
No, that's what we don't have to do. So in Christodoulou's approach, every time you take a normal derivative, you have to add a power of the of what I call J. We don't do that. So the point is that the beauty of this geometry is that the variables remain smooth, which means they actually, the only variable that needs a weight is Wn. All the others don't need any weights. And so you can close all of the estimates with 2 powers of Jg. On every, you really only need 1 power of Jg, but for L2 estimates, it's nicer to use 2 powers of Jg. So we do it with 5 derivatives, but you can do it with 6, 7, 8, 20, and it's still only 2 powers of Jg. So you don't have this issue of having to go 1 level higher every time in the weight.
Okay, I see. Interesting. Very interesting.
So somehow, sorry, Marcelo. So somehow the change of variables desingularizes the problem to some extent.
Yes, it's because when you change to these variables, the dominant Riemann variable is being carried by this 3 characteristic. And so when you move along this 3 characteristic, it's essentially frozen into its initial data. And so the Jg times the normal derivative of the dominant Riemann variable, which is the object in Eulerian that's becoming infinite. When you multiply by Jg, that's frozen into the initial data, and it just basically remains smooth for all time. The other variables are even nicer because they don't even need the power of Jg. They stay smooth on their own. And so it's very, like I said, it's very much like in the Ebin-Marsden approach. When you take Euler and you go along eta, things stay smooth. And it's kind of similar in spirit.
So my other question, Steve, is just, so if you go back to your last picture, they have the blue part that you follow the solution. Yeah. So is that just a period by domain of dependence considerations, or is like there's a singularity there too?
No, it's not the singularity. So this is the one characteristic surface, and information.
Yeah, so
information
that's just a
can't
domain of dependence consideration, right? It's just that by domain of dependence, you cannot follow the solution past that, right?
Well, you can. You see, it's okay. These equations here, when written in these Lagrangian-like coordinates, these equations here, they're written along the three characteristic. So I could actually continue these equations all the way up past that blue surface. What happens is that they're no longer valid, they're no longer physical solutions of Euler past that blue surface. So to some extent, what you're saying is true. It's just that in these coordinates, I could still continue that solution. The only difference is I can't map back to the original solution once I pass this blue surface.
Got it.
But in these coordinates, I could solve the equation all the way up to the parabola on the left.
Okay, so just a quick question. So the paper's not out yet, right? You said you're going to be posting soon.
We're going to post it at the end of the month.
Okay, got it.
Yeah, I'll send it to you.
Thanks.
I have a simple question. I had the impression that if you look at the inviscid Burger's equation, the whole thing becomes much simpler. The ALE change of variables just becomes the Lagrangian variables. And then you can easily get global existence of smooth solutions in Lagrangian variables, but they don't transfer back to Eulerian variables because the change of variables is no longer a diffeomorphism. It becomes a multi-value, a many-to-one function. Is that correct?
While it's true that everything you've said is true, except for the fact that you don't get a global solution. You can still use the Lagrangian coordinate and still get a shock solution, because for Burgers, if I just do this in one dimension, you have an explicit solution that eta of x comma t is just x plus t w naught of x. So you see, if you look at eta x, it's just 1 plus t times w naught prime. And w naught prime is roughly minus 1 upon epsilon. So what you can see is that this quantity will still go to 0 exactly at time epsilon, as you expect. But everything you said is absolutely correct. This is literally for Burgers, this would be the Lagrangian coordinate, and you would have this formula here, and everything you said is absolutely correct. So the ALE version is essentially what happens when you go to Euler. There's a bit of a tangential reparameterization makes the geometry a little bit slicker for the point of view of analysis, but it's essentially exactly what you said.
I see. Okay. I have many more questions, but can you tell me how can I get in touch with you to ask them?
Well, send me an email and we can arrange to Zoom, and we can just, we can talk
Good.
over Zoom, and I'll be on my iPad.
Thank you very much.
You're welcome.
Any more questions? Okay, if not, then let's thank the speaker for a beautiful talk.
Thank you very much, and happy birthday, Professor Adam. I wish I was there.